Pre-calculus 8.3, day 1, we are looking at inverse matrices. We're going to be using those to solve equations, kind of like we use the determinant to solve equations, just inverse matrices is a different process that we can use. And when we talk about inverses undo each other. And when you have a matrix A times its inverse, and we're going to use that kind of notation, A to the negative 1, that notation is for the inverse of matrix A. It does not mean 1 over A. So A inverse, when A is a matrix, is not 1 over A. It's not something that you can do. It's just a notation for an inverse matrix. Oops. So when you multiply a matrix times its inverse, you get what is called the identity matrix. And the identity matrix is going to be given the capital letter I. And so whether you multiply them in the order, A times A inverse, or if you do A inverse times A, this is one case where there's an exception to the multiplication is commutative, and you will always get the identity matrix. And the identity matrix for a 2 by 2 is 1, 0, 0, 1. The identity matrix for a 3 by 3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. We only have these for what we call square matrices. And that just means that the dimensions are the same. It's an n by n. It's a 2 by 2, 3 by 3, 4 by 4. A matrix has to be square in order to have an inverse. So you always, to do the identity matrix, you always have a diagonal of 1s, and then the rest are 0s. So in example 1, it says show that B is the inverse of A. Well, what we need to do is just multiply them. So we have matrix A, and then we have matrix B. And when we go to multiplying them, again, we have the first row times the column. You get 16 plus a negative 15. Then move to the next column. You've got a negative 20 plus 20. Drop to the next, the second row of the first matrix, the 3, 4, and multiply by the column in the second one. So we've got 12 plus a negative 12. And then we have a negative 15 plus 16. And that comes out to be 1, 0, 0, 1. And then we need to just show that B times A, if I change the order, I still get the same identity matrix. So if we multiply these, then we get 16 plus a negative 15. And then we have 20 plus a negative 20. A negative 12 plus 12. And a negative 15 plus 16. And we get 1, 0, 0, 1. And so we've shown that they are inverses of each other because when we multiply them in either order, you get the identity matrix. And so how do I get an inverse matrix? And there's a simple formula that only works for 2 by 2 matrix. And so the inverse we do of A inverse, is 1 over the determinant of A. So we learned how to do the determinant, and we actually use that single value in the denominator by multiplying one diagonal minus the other diagonal's product subtracted. And then we do the switch up order. And this is for matrix A, if matrix A is A, B, C, D, Notice then we take this column and switch the order, A and D switch. And then for this diagonal, you negate. You don't switch, but you negate them. So find the inverse of A. Well, A inverse is going to be 1 over, and that's where you take this product minus this product. That's how you find the determinant of matrix A. And then it is times, you take matrix A and you switch the 3 and the 4, and you negate the other column. You don't change the order. You can't really see it on this one, but that's how you get the inverse. And then we are going to take 1 over 12 minus 4 is 1/8, and we're going to multiply in. We have a 4/8, a -2/8, a -2/8, and 3/8. And then simplify, reduce. So we have a 1/2, -1/4, -1/4, and a 3/8. And that is the inverse of matrix A. So if I would go back and multiply A and A inverse, I would expect to get that identity matrix for a 2x2 if I've done it correctly. All right, so then for part B, if I do B inverse, I'm going to do 1 over the determinant of B, which is this diagonal, this product, minus this diagonal's product, which is 6, and you get this 1 over 0. It is not possible. Not all matrices have inverses. So if you get a determinant of 0, the inverse matrix won't exist for it. So this example 3, it says use matrix multiplication to check the result in 2 ways. That A times A inverse is the identity, and A inverse times A is the identity. And so I can take from 2A, matrix A, and multiply, so A times its inverse, and see what happens when I start multiplying. So I have 3 times 1/2 plus 2 times a -1/4, which is going to be a -1/2. And then I have a -3/4 plus 6/8. Then I have 1 minus 1. And I have a -2/4 plus 12/8. And when I simplify that, I get a 1. And I've got 3/4 and -3/4 is 0. I have a 0. And I have well, if I get a common denominator, I can make that, 3/4, and sorry. And anyways, that is going to come out to be 8/8 or 4/4, and it comes out to be 1. And so there, I've multiplied and I showed that it is that they are inverses. But then I can also do this A inverse times A and show that that's the identity. I want to show both of these. So 1/2. Oh, another thing you could do is for the inverse, you could leave the scalar outside the 1/8 and use the 4, the -2, the -2, and the 3 and multiply by the scalar last. So that's just using this as 1/8 for -2, -2, 3, if you wanted to do it that way. and then times A, which is 3, 2, 2, 4. And then do this multiplication first and then distribute the scalar. Just make sure you show the scalar as you go through. And sometimes that's a little nicer because you don't have the fractions. So you have a 12 plus a negative 4. Then you have 8 plus a negative 8. A negative 6 plus 6. A negative 4 plus 12. And when you multiply through, you've got 8 times 1/8 is 1, times 0 is 0, times 0 is 0, and 8 times 1/8 is 1. And it's just a little bit easier. So use matrix multiplication to check your results, that they truly come out to be inverses. In example 4, rewrite the system as a matrix equation. We're getting ready to solve systems. We did it before with Cramer's rule and determinants. Now we're going to be using inverse matrices. And so when we go to solve this, A is going to be the coefficient matrix, X is going to be your variable matrix, and B the constant. So what we do to set this up, we want this A, X equaling B kind of situation. And so the coefficient matrix is 5, 3, negative 2, negative 6. And your variable matrix is your X, Y. And your constant matrix is 4, 1. Do not write X, Y like this, because these need to be able to be multiplied, and you need a 2 by 2 times a 2 by 1. These need to match. And if you do it this way, the dimensions won't match. So that's setting up a 2 by 2, getting ready for the next lesson on solving these. If we do a 3 by 3, it looks pretty similar. The coefficient matrix, here are your X coefficients. Your Y's are 1, 3, and negative 2, and your Z's are 2, negative 1, and 3. And then your variable matrix is X, Y, and Z, and it equals 4, 5, 6. And then we're getting set up to solve these. So just setting them up.